And we are back. This particular recording will talk about not conserving momentum, but changing momentum. I mean, let's face it, sometimes you want things to go faster, or you have things and you want them to slow down. And when that happens through the application of force, you are changing an object's momentum, in which case it is not being conserved because you're either adding some or you're taking some away. So that's what the focus of this one is about, changing momentum. If there's no extra forces, you're not pushing or pulling on something, there's no friction, something like that, the momentum will not change. It will conserve. It will just, if you hit one thing into another, it will collide and transfer. Whatever one object loses, the other object gains. All right, but what about if you aren't conserving momentum? What if you are pushing on something, or you are pulling on something, or there is friction and it's slowing it down? In that case, you're going to change its momentum. And so the way Sir Isaac Newton looked at this was he said, all right, well, I know that if I'm going to change an object's speed, it's going to work according to my second law here. I know he didn't call it his second law, but this idea of F equals ma, but he rewrote it. He said, okay, that's a change in velocity with respect to time. That's our slope of the line, by the way, from all those millions of graphs that we've done, right? But he took the t and moved it to the other side of the equation and came up with this one. And it really is this. It's just written in a slightly different way. And so what we're looking at here, he called this impulse. He says in order to change momentum, you have to apply an impulse. Now don't be fooled. This doesn't really mean anything different than this. These mean exactly the same thing, which is why there's an equal sign between them. All right, and MOPS in particular is going to try to fool you all the time. If a question asks you about impulse and you see something about changing momentum, it is the same thing. It is the same answer. Okay? So how do you change an object's momentum? Well, you could change the mass, but that's highly unlikely. More likely is that you are going to change the object's speed, which is what he's referring to here. How do you do that? Well, you apply a force over a period of time, and it will change the object's momentum. And that's really all this is referring to, but it is a really handy little formula that we are going to get to use. Okay, now just a couple of, little nuts and boltsy things, right? The unit of impulse, it's got to be the same as momentum. It's going to be kilograms times meters per second. All right, it's the same thing. If you're going to change momentum, you'll be doing it with the same stuff, right? Okay, so how would you actually use this kind of information? Well, the video that you watched about car crashes gives you a whole bunch of possibilities. There's that whole egg thing, right? Ooh, eggs, Pringles. I think we might recognize some of this. When you have an object that is going to change its momentum, by the way, that's another fancy way to write it, right? That means the same thing. You're going to apply a force over time. If you want the force to go down, then you need the time to go up. Right? You need to lengthen the time of impact, which is what the whole car crash safety thing is about, right? They want the force that you notice on your body to be less. So they have airbags, they have the breakaway poles, they've got the cushions and things like that, because that extends the time where your momentum changes. And if that is the case, the force will drop. One of the ways I like to write this along these lines, right? We can either have a very small force with a large period of time, or for the same change in momentum, you can have a big force over a very short period of time. Now, the car crash video, keep in mind, is focusing on this. They're trying to get to that as much as possible. But there are situations where you want this instead. Don't be fooled. It's not always that, right? Obviously, if we're dealing with a car crash, then yes. But let's say, for example, you, I don't know, you want something to go really far or really fast. Well, you want to apply a lot of force. And as long as it's over a short period of time, it'll be the same as if you know, have the reverse situation here. But what if you're trying to hit a home run? Well, then you want as much force as possible, but you also want as much time as possible so you can get as much change as possible. Right? That's the difference between swinging for a home run and hitting a bunt. All right, there we're applying a small force over a short period of time. There we want a large force over a large period of time. It's the same thing for putting versus driving in golf or tennis. You know, those little short shots that they like bloop over the net compared to the longer ones where they're following through and there's so much more time of contact with the tennis racket. All of those things are changing the momentum of the ball. Okay, and so you maybe want to minimize it or maybe you want to maximize it. It just depends on what you're doing. Okay, so how are we going to use this? What are we going to do with this? Let's take a look. Here's a typical type of a problem where you're trying to figure out how much force something is going to endure in order for something like this to work. So I'm going to say, all right, force times time is the change in momentum. Mass times delta V is also the change in momentum. They mean the same thing. Remember, this means change. All right, I could write it as one long one, but I haven't looked at this question yet. I'm not really sure what I'm going to get. So let's see. I've got my mass right here, 52 meters per second. We're trying to stop it. Okay, so I know my final velocity is going to be 0. I know that this is my initial velocity. I've got a time given to me here. What is the average force exerted on the ball? Okay, I guess I am using all parts of the equation. I might as well. All right, we'll just set them equal to each other. So I'm looking for force, which means I'm going to divide by time on both sides and solve for force. Now, let's keep in mind that this always means final minus initial every time. So 0.25 kilograms. All right, my final velocity is 0. My initial velocity is 52 meters per second. And the time is 0.10 seconds. Okay, so this is what I'm going to get a negative answer. Okay, so I'm going to get a negative answer. That's fine. I'm going to get negative 130 newtons. Now, obviously, if you're doing a multiple choice question, negative 130, positive 130, that's a matter of direction. But see how this formula lets you solve for missing pieces. Maybe you want to solve for the amount of time. Maybe you want to solve for the new final velocity if you know the force. Maybe it's not stopping. You never know. You never know. All right, let's look at this one. I want to take just a few minutes and take a look at some of the things that MOPS puts in here. So I grabbed a couple of MOPS questions, as a matter of fact, because this unit, it's tricky. All right, sometimes they're talking about two things hitting each other. Sometimes they want to compare two separate collisions. Okay, so this is a typical one. If I read this question carefully, and if you need to, stop and pause and read it before I go through it, right? But they're talking about two separate collisions. They've got a wall, right? And they've got ball A, and here's ball B. All right, here's situation B. And it says ball A hits the wall and rebounds this way with a speed of 4 meters per second. I'm going to make it negative because it's going the other way. All right, so let's, oh, it says the initial speed of 5. If it rebounds and it goes the other way, that means it's negative 4. Ball B hits the wall and stops. Okay, so here's ball B. It's a separate ball. It's still moving at 5 meters per second, but it just stops, falls down, right? So final velocity of 0. And then they ask these questions. They want you to compare it. Velocity change, momentum change, impact force. Ooh, these get so tricky. Okay, so let's consider velocity change. That'll be my first one. All right, they're asking you, what is delta V? Delta V, as you know, as I've just said, as I've said multiple times in class, it's final minus initial. And direction matters. Negative 4 minus 5 gives you negative 9. All right. 0 minus 5 gives you negative 5. This one has a greater velocity change. Rebounding always has a greater velocity change. All right. So ball B has less velocity change. Or actually, you know what? I'm not even going to write B. Let's change that. Less velocity change. What about momentum change? Well, how do I find momentum change? Momentum change is either going to be force times time, or it's going to be mass times change in velocity. Well, considering this one has less change in velocity, they're the same mass, this one is also going to have less momentum change. What if this question, instead of saying momentum change, said impulse? I'd still answer the same question. I'd still answer it exactly the same way, because they'd be asking the same exact thing. Momentum change equals impulse. They are the same. All right, impact force. Impact force. This is tricky. Okay, so let's consider. Right? So I don't know. Maybe the easiest thing for me to do would be to make up a number, or maybe not. All right, let's say that's ball A, and let's say that that is ball B. All right, hits the wall and stops. Assume the collision times are the same. Okay, so ball A, we have said, has more momentum change. This one had less momentum change, right? And the time for both is the same. Right? The question tells me the time is exactly the same. So this answer is going to be bigger. This answer is going to be smaller, right? Because this could be 100 over 10, and this could be 10 over 10. You know that this answer is going to be smaller than the other one. And so this one would have also less impact force. Okay, now maybe that makes sense. You're like, yeah, okay, that wasn't any big deal. All right, but that is, you got to keep in mind, what are they doing here? They're having you compare two separate situations, because then they're going to give you a question that looks like this, and then you're going to get all twisted up, because I see it every single year. A bug encounters a collision with a high-speed bus. So these are two objects crashing into each other. It is a single collision. So, you know, my bus looks like a truck, right? And here's the bug, and it hits the truck, and the truck hits it back, right? And we want to know what the heck is going on. We want to know about force, impulse, momentum change, and acceleration. Okay, they are hitting each other. If they are hitting each other, we have to consider Newton's third law. For every action, you can finish it for me, right? I can almost hear you in my head. For every action, there is an equal and opposite reaction. So the bus and the bug hit each other with the same force. You say, what? That doesn't make any sense, because the bus is so much bigger. I know, but we'll get to that. The forces are identical, okay? So that's the same force, right? It's the two things. Now, granted, if I was talking about a bus hitting a wall and a bug hitting a wall, this answer may not be the same thing, all right? But they are hitting each other. That's kind of important, all right? Now, if they are hitting each other, the time of impact also has to be the same, right? How can the truck hit the bug longer than the bug hits the truck? How can the bug hit the truck longer than the truck hits the bug? That makes no sense, right? It's hard enough to say it, much less imagine it, right? So they have the same amount of time, right? So that means their times are also equal. So guess what is the same for both of them? Their change in momentum, right? Those two numbers are identical for the bus and the bug. So that means that their change in momentum is the same. And anytime I see change in momentum, I know that that means impulse at the same time, right? Those are all the same. So why does the bug go splat? Why does the bug go splat? Because it's not the force that hurts you, it's the acceleration, right? Because F equals ma, and we know that the bus is huge, so it's going to have a really tiny acceleration compared to this mass. This bug is so tiny, it's going to have a huge acceleration because my forces are the same. Okay, so what do I want to know about the bug? Greater acceleration. Okay, MOPS is going to try to fool you. The first thing to figure out is, are we talking about two things hitting each other or two separate types of collisions we have to compare? After that, if you have things that are hitting each other, Newton's third law applies. The only thing that is different is acceleration. All right, the time of impact is the same, the force of impact is the same. Therefore, the change in momentum must be the same impulse. It's the accelerations that will be different. All right, hopefully that is a little bit helpful to get you started with some of the finer points. MOPS is going to test you this time, but I am confident in your abilities to sort it out. Let me know if I can be of service and help you out. Talk to you later.